Cats. So normally I just find an Edpuzzle that shows you how to do this, but apparently I make my mole map backwards from everybody else. So if you missed class on the 22nd or 23rd, this is the last portion of the guided notes that we made that's not included on the guided notes. This is what we call the mole roadmap or the mole map. This is something that will be available to you when you take your quiz over these two-step mole conversions next class, as well as on your Unit 6 exam. So previously we've been talking about how we use our resources, i.e. the periodic table, to go from that which we can measure on a balance, which is grams, to that which we quantify in groups of atoms or molecules called moles. And the whole point of doing that was to be able to go from what we can measure on the balance to count that which we cannot see, which are atoms, if it's an element, also sometimes labeled as molecules, if it's a compound. So this is adding one more step onto the conversions that we learned how to do before spring break. So what you already know how to do is to convert in between grams and our grouping of atoms called moles. So if we're going to convert in between grams and moles, you guys know that we use the molar mass. Where do we find the molar mass? POW, periodic table. Remember, that is the number on the bottom that tells us how many grams of that element we need to put on the balance to have a full mole. So for example, silver, 107.87 grams, give us a full mole. So the units on molar mass are always however many grams for 1 mole. And that is on the periodic table. And we talked about that the mole is number 1. 1 always goes with the mole when we're doing these conversions. That's going to hold true when we take it to the house and go moles to atoms or molecules. So the last step, or the last conversion factor or fraction that we use to get in between moles and atoms, is that big number that's above the board in my classroom, Avogadro's number. And remember, that's a number sign, not a hashtag, because I'm old. And that is always, no matter if you're talking about elements, compounds, whatever, is 6.022 times 10 to the 23rd. That's how many particles, or anything, are in a mole. Notice that I left a blank for the unit. That unit will be, if there's one element, one capital letter, we use the unit of atoms in the blank there. If there are 2 or more elements bonded together, that's what makes a compound. So like H2O, NaCl, we use the label of molecules. But the number's the same no matter what. By definition, that's how many anythings are in a mole. So to use this mole map to convert between that which we can measure to that which we cannot see, we need to ask ourselves, where are we starting in this map and where do we need to end up? So I'm going to go ahead and do what I did in class today, which is use a homework problem to show you how this works. One of the problems that we did in class, actually from our notes, I'll go ahead and work for you. The question was, we had 100.0 grams of H2O, and we wanted to know how many molecules of water that was. Well, like any good dimensional analysis problem, we're going to make that a fraction, and to make a number a fraction, we put it over 1. And remember, that's S for sample or nothing. The unit that we want to get rid of always goes in the bottom of the next fraction. That's called cross-canceling. So I don't want to know grams anymore, so I'm going to put that on the bottom. Now, I kind of got ahead of myself. If I'm starting in grams here on this mole map, I need to figure out how many molecules that is. So what you'll see is that is a 1-2 step conversion. You already know how to do the 1-step conversion. Moles is like our translator in between grams and atoms. Okay, so we can't get from grams to atoms without first going to moles. So moles is going to go on top of that next fraction. Now remember, whenever we do this, we always put the units where they go first, then we let the numbers follow the units later. I'm not done yet though, because I want to know how many molecules that is, so I'm going to need one more step. That means that the moles I don't want to know, those are going to have to go on the bottom of the next fraction to cancel out. Since I want to know molecules, that's what's going to go on the top here. Look at that abbreviation for molecules. MOLEC. Don't confuse it with the mole. As we do this, and like I've always said, and if you look at the factors we've made, the mole is number 1. 1 always goes with the mole. So that's easy enough. Atoms or molecules is always Avogadro's number. Doesn't matter if it's an element or a compound. So that's where I'm going to put my 6.022 times 10 to the 23rd. Now we know we have to go to the periodic table to get the mass in grams. Since water's a compound, I'm going to have to do some math on the side to figure out what are all of those atoms added together for their molar mass. If it was just one element, if it was just, copper, I would just take the number from copper on the periodic table. Spoiler, that's problem number 1 on your homework assignment. So out to the side, I'm going to find the molar mass of water. So if you need a refresher on that process, we break the break the compound down into its elements, capital letters to tell us that. You all know that there's hydrogen and oxygen in water. The 2 tells me that there's 2 atoms of hydrogen. No number tells me there's 1 atom of oxygen. We'll find the numbers for hydrogen and oxygen in the periodic table. Hydrogen is 1.008, oxygen 16.00. So we multiply the number of atoms by their individual molar masses. We're going to multiply that out. Don't forget to multiply the 2. I'm going to be a little bit lazy and add all of that together. Once I do that, I'm going to get 18.016. And since that's the molar mass, the mass of a mole, that's how many grams are in 1 mole. So that 18.016 is what's going to go right here. Again, if it's just one element, you don't have to do this work out to the side. You would just find the element on the table, put its number there with grams. Now this is just business as usual. You all know that we need to multiply our numbers straight across the top and our units, straight across the bottom with our units, and then divide. The one tricky thing that we have to add to this process is that whenever we're doing something with scientific notation, we have to put math hugs around those numbers. We need some parentheses so we keep the order of operations set. So I'm going to grab my calculator here. Now I'm going to show you the multiply it all the way across the top and bottom and then divide, for those of you that need to see that. The rest of you probably know that if you multiply or divide by 1, it's not going to do anything. So if you want to skip that step, you can multiply the numbers that are on the top, divide by the numbers that are on the bottom. And since multiplication and division are inverse operations, it doesn't really matter what order you do it in. So as I punch it in my calculator, across the top I'm going to get 6.022 times 10 to the 25th when I multiply 100 by 6.022 times 10 to the 23rd. My units multiply as well. Grams times moles times molecules. 1 times 18.016 times 1, 18.016. Sample times grams times moles. Hey, what cancels? Like when we learned how to do first step problems, grams cancels, but now moles cancels as well. So the unit that's left on my answer will be molecules. What's left is to divide these numbers. Again, don't forget some math hugs around your exponent, scientific notation. If you don't know how to type this into your calculator and you need some help with that, let me know. It's different depending on what calculator you're using. So if I divide those numbers, top divided by bottom, I get 3.342584369 times 10 to the 24th. Your calculator might say E. E means the same as times 10, so just swap that out. That's molecules of H2O. Before I worry about significant figures, I'm going to ask myself if that answer makes sense. I'm starting with 100 grams of water, and if I compare like units, that's more than 18, so that means I must have more than 1 mole's worth, so my answer must be more than 6 times 10 to the 23rd. What makes my answer more? Pow, 24. Bigger exponent, bigger number. So logically, this answer makes sense. Significant figures, remember we can't be more precise than the sample. Just like when we used an infinite number of significant figures with the periodic table, we're going to do the same thing with Avogadro's number. So our sample will always limit us. And since there's a decimal point here, That would be 1, 2, 3, 4 significant figures. For scientific notation, we're just going to round the number in front of the times 10 to the 24th. So I'm going to count 1, 2, 3, 4, stop at the 2, and if I peek after, that's a 5. So what's that going to do to that 2? Round it up. Now a lot of students make the mistake of stopping here, and they'll be like, oh sweet, 3.343 molecules of water. Hold up, you can't have 0.343 of a molecule. That's some crazy nuclear chem going on, and you should probably run. We need to have that times 10 to the 24th because that makes that number a whole lot bigger. And it makes sense, right? Molecules are super tiny. So don't leave off that exponent. And then we get the number of molecules in our sample. So you have the technology. You already know how to do these skills. We're just adding the additional step of going from moles to atoms or molecules. And guess what? The number is always 6.022 times 10 to the 23rd. It's your new favorite number. Put it on a jersey. So how does this relate to the homework? Well, I gave you 7 problems to do on homework 6.3, which is called two-step mole problems. You can find that probably right underneath where I've posted this video on Canvas. This is how we go from grams to atoms or molecules. To go back the other way, the process is the same. So what we did in class was, from this homework, we worked problem number 7. What is the mass in grams of 8.97 times 10 to the 23rd molecules of, oh boy, there's some Unit 5 action right there, ionic compound, polyatomic ion, not a transition metal, barium hydroxide. So let's work that problem out here. We're starting in molecules, that's what we're given. We're trying to find grams. So we'll start with the number that we were given, which is 8.97 times 10 to the 23rd molecules. And that's BaOH2. People say 6 do I have to label that? It's good practice, so why not? No matter which direction we're going in this mole map, we always make it a fraction by putting it over 1, sample or nothing. Now in this case, I can't go directly from molecules to grams. I have to go to moles first. Well, you need to cancel molecules, so it has to go on the bottom of the next fraction. Put the numbers after we put the units where they go. We'll let the numbers follow those units. I can cancel out molecules, and then I can get from molecules to moles. So moles will go on the top of the next fraction. But we're not done because the problem asked for grams. So that's when our second step comes in to go from moles back to grams. In order for moles to cancel, it has to go on the bottom of the next fraction. Then the grams we're looking for can go on top. What number always goes with the mole? The mole is number 1. So half of this fills in itself. How many molecules are in a mole? Right here. I got 6.022 times 10 to the 23rd, always and forever. Here we go. The number of grams, where do I go to get that? Got to find my molar mass on the periodic table, and just to be super extra special, we have to find the molar mass of barium hydroxide. Looks like I got some space up here, so I'll do that here. Step 1, break it down into the elements by capital letters. Barium, oxygen, hydrogen. Step 2, count how many we got. This barium's not in those parentheses, and there's no number next to it, so that means there's only 1 barium. Just like in math, when you got a number outside parentheses, we distribute inward. We just do it backwards. So that means we've got 2 oxygen and 2 hydrogen. We multiply those by their masses from the periodic table. I'm going to be lazy because I've already got hydrogen and oxygen written over here. So oxygen is 16, hydrogen is 1.008. And if we find barium, right down here, 137.33. We'll multiply those out and add them all up. So 137.33 plus 32 plus 2.016. 171.346 grams for every 1 mole. Because remember, periodic table is the mass of 1 mole. So then we let the numbers follow the units. That 171.346 goes here with grams. Now those of you that are like 6 I hate showing my work, do I really have to do the multiply all the way across the top and all the way across the bottom and divide? No. This is the bare amount of work I would need to see from here to here for you to get full credit for showing your work. Okay? And you know that multiplying and dividing by 1 doesn't do anything, so when I'm doing this in my calculator, remembering math hugs of course, I'm doing 8.97 times 10 to the 23rd divided by, parentheses, 6.022 times 10 to the 23rd, I hit enter, times 171.346. That's how I do this. But again, just to show you how everything works out when we do the math all the way across the top and bottom, I'll show you how that goes. Parentheses, 8.97 times 10 to the 23rd, end parentheses, times 171.346. On the top, I got 1.53697362 times 10 to the 26th. Remember, if you see an E, that's the same thing as times 10. Don't put an E, put the times 10. My units, kind of ran out of room here. Molecules times moles times grams. That's my top. Across the bottom, 6.022 times 10 to the 23rd times a whole bunch of ones isn't going to change anything. I got sample times molecules times moles, running out of room. What cancels? Molecules and moles. Sorry it got dark. Apparently I've been sitting too long. I love automatic lights. All right, back in business. So what do we do now? Everything cancels except the unit of grams that will be in our sample. Now we divide top by bottom. Don't forget parentheses. Don't forget your math hugs. If you forget your math hugs, you're going to get some crazy exponent like to the 47th or something, some crazy high number. And that's not going to make sense because the idea of getting to grams is it's a number that we can physically put on a balance without dying. And when I divide these two numbers, I get 255.226439.7 grams of barium hydroxide. Does that answer make sense? Well, I've got almost 9 times 10 to the 23rd molecules. That's more than 6 times 10 to the 23rd molecules. So that means I must have more than 1 mole. Remember, these are equivalent. If I have more than 1 mole, I must have more than 171 grams. That number's more, not too much more, so that makes sense. And I could put 200 grams on a balance without breaking it. Significant figures for scientific notation, remember it's what comes before the times 10 to the 23rd. So I've got 3 here, so I'm going to count 1, 2, 3 numbers in, stop at the 5. After the 5's a 2. So we're going to round that to 255 grams of barium hydroxide. And that's how we use the mole map to convert all the way from grams to moles.